Okay, well, now we know how to build wave packets. Let's see if we can describe how wave packets propagate through space or evolve in time. All right? It sounds a little esoteric, but it'll be very important and it'll fit right into our discussion of uncertainty. Okay, here's the idea. The evolution of wave packets, or the propagation of wave packets, it depends critically on how the wave speed depends on frequency. Okay? You might imagine two different cases. First, light moving through vacuum. When light moves through vacuum, the wave speed, the speed of light, is independent of frequency. Okay? However, when light moves through glass, we know that the wave speed does depend on frequency because the index of refraction of glass depends on frequency or wavelength. That's why prisms disperse light. And this whole subject actually is called dispersion. So here's the idea. If the wave speed is independent of frequency, then the wave shape remains constant as it moves through space. That is, our wave packet, which maybe looks like this, even though it contains many different frequency components, if they all move at the same speed, then, well, later on the wave will look exactly the same. Okay? On the other hand, if the wave speed depends on frequency, then the wave packet shape will change. Okay? And maybe that's easy to understand too. We start with a wave packet that's composed of many different frequencies. If each of these frequencies propagates at a different speed, then later on, well, they'll get out of step with each other. The fast frequencies will get ahead of the slow frequencies. We might end up with something like this. Oops. Oh, let me try that once more. It decided I wanted a straight line. Here, we've drawn a case where the high frequencies are getting ahead of the low frequencies, and so the wave gets stretched out or chirped. The word chirped comes from this process occurs in the radio when radio waves bounce off the ionosphere, and as a result, a pulse turns into a chirp because different frequencies arrive back at the same time. Anyway, notice something interesting. The width of the pulse has changed. See that? Of course, that's important for our discussion of uncertainty. All right. Well, I want to show you a simulation that illustrates this. Hang on, and we'll take a look at that. Okay, here's a simulation which shows how a wave evolves in time as it propagates through space. All right? And first, let me simulate a wave moving through a medium where the speed of propagation is independent of frequency. There it goes. Not so exciting, is it? The wave shape doesn't change as the wave moves, it just moves through space. Now, let's take a second case where the wave speed does depend on frequency. All right? And here the short wavelength components will be moving faster than the long wavelength components. Here, take a look. All right. Did you see how different that is? First of all, as the wave moves, the short wavelength components get ahead of the long wavelength components, just as we said. And because of that, the wave spreads out. The width of the wave pulse has increased. All right? Here, let's run this again. Now it's evolved for even longer time, and the wave is even further chirped. That is, there's a greater separation between the short wavelength components and the long wavelength components. And this occurs because in this model that we're simulating right now, the wave speed depends on the frequency. Okay? All right. So that illustrates something about propagation of wave packets. And the main thing I want to show you is that the uncertainty in position is growing with time. That's something we're going to come back to in class. There's one more thing I want to glean from this, and to see what I'm talking about here, you're going to have to look closely. I'm going to show you that the wave packet has two different speeds. One is the speed of the whole envelope, and the second is the speed of the crests of the waves. Yeah, I'll run this a couple times so you can see it. Okay? Now try tracking the wave envelope. It moves pretty quickly. But now look at the crests of the waves. Are they moving at the same speed as the envelope? They're falling behind. The envelope is kind of moving through the wave crests, if you like. Okay, so that's a feature of wave packets that exhibit dispersion. The speed of the crests of the waves, what's called the phase velocity, is different than the speed of the envelope of the pulse, what's called the group velocity. So wave packets that exhibit dispersion have two velocities, not one. They have a phase velocity and a group velocity. So now I'd like to turn and talk about that. Okay, hang on one moment. Actually, let's take this up in the next video.